folks, welcome back. We did look at a few wireless technologies, particularly we looked at the IEEE 802.15.4, basically the MAC and PHY which is defined by the IEEE, and a stack which is built on top, which is typically the ZigBee stack, and applications can use the ZigBee API and then start using building applications using this particular radio. Now the design aspect actually comes by looking at why should I choose this particular radio as against another radio, right. And if you recall, we showed about the picture about the SOC. If you look at the SOC that we know very well now, we have the microcontroller and then you have the radio. I will remove the remaining parts for the moment, okay. I have not put that. You have ADC and you have GPIO, these are all the GPIO ports. We can quickly write them though, and this is the SRAM, then you have flash, then you have power supply, we can put here LDO, you can put DC. So I will call this the power supply block. Then you have the oscillator block, this can be either internal or it can be crystal or it can be completely external from the board, any one of them. So okay, so all of them are connected and so on. Now this radio here, whatever gets integrated into an SOC typically are, you can either have Bluetooth low energy radio or it can be ZigBee, and sometimes it can also be Wi-Fi which is embedded inside the system. Now question is when to use these, it has always occurred to you. Well, you can look up several pieces of literature to find out that, but at the same time I am interested in telling you within ZigBee itself there are several standards, okay. There are several versions of ZigBee, what is called the MAC behavior. The MAC behaviors actually hold the key to using ZigBee in the most effective manner. So the choice really is here, what type should I choose, and this is just an example, right. One is broadly you can go between Bluetooth, ZigBee and Wi-Fi because of its capability in terms of range, okay, and this has huge advantage of low power, extreme low power. This is also low power, and this is not low power and immune to noise. This is very critical of ZigBee. Well, BLE is not all that agile to noise, but of course it is also providing you certain features like channel hopping and so on. And ZigBee by the way also has introduced channel hopping, I will come to that very soon. And this offers you higher data rate though, 1 Mbps, 2 Mbps and so on, much greater than even 2 Mbps nowadays. But ZigBee says I will not give you anything greater than 250 kilobits per second. Wi-Fi of course gives you much higher data rates, and higher power consumption. So on. Now there is a certain flavor for IoT where you have to understand the commercial IoT versus the industrial IoT, okay. Now that differentiation comes in the following way. If you look at the commercial IoT, we look at stuff like air quality that you want to measure, the fitness band that you know very well, the pedometer applications which essentially do step counting, all of them essentially are revolving around how to improve quality of life, how do you save time and how do you save money and so on. This is mostly human centered and something that will benefit humans, even if it is automated, it is mostly to benefit the humans. The industrial IoT is mostly to benefit manufacturing. As you can see here, This is about integration of OT, which is the operational technology, basically monitor in a high level view, you can say it is monitoring the machine status and health when you talk about the OT, and the IT part, which is the information technology part, essentially tracking the usage of these systems, of this equipment and so on. So, essentially it is industrial IoT is essentially bridging the two, it is combining both the OT and the IT part and providing you smart machines, network sensors, analytics and all that which are because of this merged behavior merging integration of these two technologies. You make machines smarter by using network sensors, you can collect lot of data, perform data analytics so that it can improve the business to business service and so on, right. You can also do machine to machine interaction, process monitoring for instance is a very good example, vehicle fleet tracking and so many other related applications are there. Good thing about the industrial part is that they are self organized systems with distributed control, essentially autonomic industrial plants form the networks which are used there are essentially self organized systems with all this control built into the networking infrastructure right then and there. So, the requirements for communication are completely different folks. Here is where the design comes in. If you are looking for very low latency throughput and all that which may be required for the industrial environments, then you may have to look at IIoT technologies, right, whatever is most suited for IIoT communication. If it is for air quality and let us say the pedometer kind of applications which humans are involved, then it may be a different requirement in terms of quality of service. The commercial IoT communications are typically machine to user, as I mentioned it is user centric. Of course, there is client server interaction, but by and large it is out there where you are interested in battery life, low power, ease of installation, cost and all that. The industrial IoT is not like that, it is trying to look at timeliness, which is very critical, reliability, because if you have a problem with the process plant and if there is an error in the process plant, you want everything to be detected in high speed and ensure that you do not waste resources by moving on with the process in the assembly chain or even the manufacturing chain. So, these things have to be monitored in real time. Okay. So, that essentially means that those sensors that are applied there have a different criteria in terms of reliability, in terms of quality of service and so on. And therefore, the communication network there also has to be very different. You must be able to go beyond just the not just meeting the stringent deadlines, but you may also have to be robust to packet losses and you must be safe to and resilient to any damages that might occur or any vandalism that might occur to these systems accidentally, which clearly indicates that the requirements for latency and jitter are completely different. Supposing you have one packet, this is packet 1, which requires a certain amount of latency between, let us say first let me put the abstraction, this is node A, this is node B, let us say, and then there is a packet which starts from here and reaches here, and then maybe there is a acknowledgement back from here, but for the moment let us just see one direction. Okay. Now, A to B essentially has there is a link between the two, right, there is a link here and there is a link latency, and you need to measure this link latency. I will show you what exactly this jitter means when we talk about latency. See, latency is, let us say first packet comes here and exactly after some time the second packet should come and exactly after that the third packet should come and so on. It turns out that because of network okay, this is not even, so let me bring it maybe a bit closer so that it gives you a feeling that they are even. It is possible though that one packet might come here, okay, so you can see the spacing is not uniform. It is also possible that a packet can come here, which means again this spacing is not uniform. Okay. So, essentially we are looking at what is the average delay and how much is tolerated in terms of variance in the delay. Okay. So, essentially how do you calculate that? Take the average delay which is let us say x bar, okay, and take every sample 1, 2, 3, 4, 5, 6 and so on, you keep getting. You take the sample here, this is xi. So, you take xi, you would have a priorly calculated the delay, the average delay which is x bar. So, you take the square of it, you divide by n minus 1 and you sum it, sum it over all the samples. So, essentially you can put a summation here, okay. This is your jitter calculation, okay. This is just for just let me put it as this, okay. In fact, you should be using small x. So, let me be precise and put a small x. So, basically you can be talking about sample variance, this is actually sample variance. You will also have population variance, and in population variance you will be using n instead of, you will be using n here in the dr, in the denominator, n in the denominator, but n minus 1 in the case of sample variance. Anyway, so just to tell you that the jitter here you can see in this picture here is less than 2 milliseconds if you are talking about medical applications. Remember I was telling you about tactile CPS right in the first class, you can see the kind of jitter that is expected, and depending on what type of medical surgeries systems you are building with haptic and all that, QoS requirements for that specific application can be as low as 10 to a maximum of 10 milliseconds. So, you can see average, these are all average numbers, what you see here is average. But if you go down a little bit to the automotive applications, you will see that things are in microseconds, not even in milli. Jitter has to be almost in very close to microseconds, and this is a very important requirement. Now, do wireless technologies that we are discussing actually support this is the question. That is the link to what I was trying to tell you. Now, so you need as we discussed here, we need reliability, and we also need latency control, right. I will simply say latency control, which essentially means average latency and also the jitter associated with the latency. Both should be well under control, otherwise you cannot really call it, you cannot use the technology for any industrial applications. Okay. Now, having okay, I will not go into this detail, but if you want to support anything like that folks, there is only one way. You have to examine and evaluate the wireless technologies. For your application, very very important. Now, you must first of all be aware what is out there, so that you can start evaluating them, right. So, that is another important requirement for you. So, to do that I will introduce you to one more MAC behavior standard, okay, and that MAC behavior standard is the IEEE 802.15.4, which we know well, E-TSCH. There is a reason why I am writing it this way. This is called time synchronized channel hopping, very very well suited for industrial applications. Okay. Now, you have to be very careful when you talk about industrial applications. you can be talking about deterministic latency, or you can say low latency. Which one of them is 15.4e? Well, it is deterministic. What does it mean? It means you will get latency, all right, but it will always be something that is hard. You know it a priori, you know that latency. Then it is called deterministic latency. That means you are able to determine the latency and you are very sure that the wireless technology will give you that. Now that kind of latency may not be suitable in several situations. Let me give you one instance. Take the case of fire. Take the case of fire in a room. God forbid, but there is fire. That fire detection, let us say you deploy a technology which is deterministic. That means that sensor which is connected to this deterministic network will be given an opportunity to transmit every 1 second, let us say, because that is fixed, it is deterministic. So what is the latency? Latency is under control. Latency may not be suitable for this application, but it is under control. Every 1 second for sure you will get access to that fire detection sensor. 1 second is like 1000 milliseconds, please note, it is in fact it is 1000 milliseconds. Let us say so you have 1 second, you can get the data from the fire detection sensor, but you need only, I think it is around 150 milliseconds for humans to catch fire and also reach 3rd degree burns. 3rd degree burns can actually happen in 150 milliseconds. So if you say I have a deterministic wireless network which can do fire detection, this is not going to work at all, folks, right. You need low latency, you need a MAC behavior, you need a media access control behavior where the application gets low latency, that means lower than some number, and in this case it is lower than, has to be much lower than 150 milliseconds. If you have to target 150 milliseconds latency, the whole system should perhaps from detection to transmission to the actuation, from detection to communication to actuation should be less than 150 milliseconds. Now if your detection is good but your communication comes every 1 second, it is no good, right. So that is what we are trying to say. So if you have to meet this hard deadline, you need a medium access control which will give you low latency, and that is what we are to our target is indeed. So let us see, while we do not have time to really look at the low latency part, I can excite you on the deterministic latency part, and essentially the 15.4e TSCH standard, which is a very important thing, not suitable for fire detection if you are doing 1 second, but if you are doing fire detection every 50 milliseconds, but still using the DETC, right, still using 15.4e, then it is okay, you do not have to worry about it. So how you plan the 15.4e systems to meet application requirements which are like the fire detection kind of systems, is where the real design of the IoT node, the design of the radio choice and so on actually start playing an important role. So, let us get into the details. Let us get into the details of IEEE 802.15.4e dash TSCH, time synchronized channel hopping. Great. So, for that let me direct you to this nice paper which I was reading, and this paper is about IEEE 802.15.4 in a nutshell, survey and performance evaluation. So, I am sure by reading this paper you will be excited to understand what I was trying to get at when you want to choose a technology for your wireless technology for your application. I mentioned to you about the MAC behavior, and TSCH is one such MAC behavior. DSME is another MAC behavior. Low latency deterministic network is another behavior. Please note I had shown that here this is LLDN in a way, this is LLDN in a way, okay. And what we have shown here is TSCH, this is TSCH, great. So, all these things are there, and DSME is another type of MAC behavior, and TISH, both of them were incorporated as latest as 2015 and released in 2016, and essentially several issues open for investigation, including analysis of protocols under different settings, scheduling of flows in the time frequency domain, delay bound analysis and so many other related advantages with this system. Alright. So, I will skip the 15.4 part of it because we had primer already. This is 15.4e for you. Wireless communication protocols, when you talk about it, you have video, voice and data and all this. Essentially you are trying to trade off between several properties such as throughput, latency and energy efficiency with and radio coverage, targeting well defined application scenarios, right. See, the wireless sensor networks usually do not impose any requirements of bandwidth, but they require long lifetime. I am sure you appreciate that sentence, because in the sensors world we are always talking about 10 plus years of lifetime for these systems. Okay. Now, this is just an overview to start you up on this, and when you go down you realize that all these are something specific to the 15.4, particularly figure 2 is something very specific to the 15.4 system. The 15.4e for instance, it provides enhancements, and the enhancements are quite significant. In any case, the generic enhancements are the following. First one is multi-channel access. Okay. See, the problem with the Zigbee system which we studied, there is one problem that you only have a single channel for your complete PAN system that you set up. Okay. You have a PAN coordinator and all nodes identify the PAN coordinator, and then they communicate to that PAN coordinator, which means out of the 16 channels which are supported, only one channel you will be using all the time. That is a very restrictive thing. So, therefore, you must find a way to sort of exploit the remaining channels as well, right, and 15.4e does exactly this. It does channel hopping, and it does channel adaptation mechanism, so that it can battle interference, it can battle fading on the wireless channel and provide you very good connectivity. So, you can see already it is moving in the direction of being reliable. Okay. Then there is this concept of information elements which is already there in the 15.4, but not well spoken of. Okay. Now, the IE is actually part of the MAC frame, and this has been introduced to support the various MAC behaviors. the frame will look identical, but the MAC behavior will be different. So, you have an information element which says this is 15.4, this is 15.4e TISH, this is 15.4e LLDN, this is 15.4e DSME and so on. So, all these things have to be differentiated, and therefore, that information element essentially takes care of that. Now, low latency and low energy are important hallmarks which are suitable for you need that for the industrial control systems. The 15.4e allows devices to operate at a low duty cycle though, and the synchronization is a very important thing in this system. That is how you get determinism in the whole thing. So, you can think of the whole MAC as deterministic MAC because there is synchronization SY synchronization is the key here, and you can either do you have a transmitter, you have a receiver, you either transmit whenever there is a beacon, whenever there is a beacon transmission, the receiver can adjust its clock, okay, exactly aligning to the transmitter's clock. Either you can do it with beacon or you can also do it the other way, right. You can have one clock here, this guy will also have his own independent clock. Now, the ACK packet which goes in this direction, unlike this which can be either beacon or data packet, here you are getting only ACK, okay. This is the same node A to B and this is A B, but this time it is B to A which is a small ACK packet. Now, A can adjust to B's clock, either you adjust B to A's clock, B to adjust to A, or A to adjust to B. B adjust to A is transmit driven and A adjusting to B is receiver driven, both are possible, and all these mechanisms are built into the system here. Then there is the third one which is multi-purpose frames. Basically the advantage here is the frame formats of all MAC behaviors are based on the peculiar features of this MAC behavior and its targeted applications. So, it is another important feature. You are not just configuring one type of frame, but you will be able to embed different MAC behaviors into that frame itself. Essentially the IE is doing that, right. So, it is giving you that feature and essentially that is what is mentioned here. Of course, the IE contains which MAC behavior is there. So, it is easy for receivers to know what is the way the transmitter is actually thinking. Apart from that, the enhanced beacon is an important thing. We had beacons in the 15.4 world, here we have enhanced beacon, and this EB carries information about whether it is time synchronized channel hopping and low energy are enabled, and information about the respective channel hopping sequences, all that is held in the EB part of the beacon. So, it is not the old beacon we knew in the 15.4, but it is indeed the enhanced beacon format. Also there is MAC performance metrics which are supported by just the feedback. You can basically infer the number of transmitted frames that require one or more retries for acknowledgement, the number of transmitted frames that did not result in an acknowledgement during a term called MAC max frame retries and so on. So, lot of stuff, a lot of interesting enhancements have been done to the basic MAC. So, one can read this article and get into the details, but I think what is important for you to skip all this section and go directly into the section related to time synchronized channel hopping. Now it will actually tell you the 15.4e TSCH, where can it be applied. Okay. We will get into the details of that, understand that in a little more detail. Let us just look up the TSCH MAC, which I mentioned is a MAC behavior. The MAC behavior of interest to us for several industrial applications is the time synchronized channel hopping MAC, which is nothing but 802. So, let us put it technically correct, IEEE 802.15.4 E dash TSCH. You must not forget this, because you can have dash DSME, you can have LLDN, so on, right. So, we are only worried about the TSCH implementation. Now, as I mentioned to you, the main implementation of this MAC TSCH MAC is not a straightforward thing. However, there are two implementations available to you, two implementations available. Okay, two implementations are there. One is under OpenWSN. This is again from Berkeley, UC Berkeley has this, and the other one is on Contiki, OS, and both of them have the support for this 15.4e. But before we get into the detail of that, I think what is important is to know a little more about the protocol itself. Okay. So, let me show you what exactly TSCH does in its and how it is able to, how the beauty of this TSCH protocol and its ability to provide you some reliable communication, high reliability. Okay. So, let me point you to this paper here. This one says that the TSCH protocol is MAC behavior, it mentions, and it provides reliability and critical assurances, and it says that it can apply it for networks such as oil and gas industries and so on, wherever critical say safety critical applications are of prime importance, and it does frequency hopping, and that supports a mechanism which greatly improves the reliability of the system, right. And okay, when you do frequency hopping, you are not transmitting on just one frequency, as I mentioned earlier, it is able to hop across a frequency, and there is a schedule for hopping. Time slotted communication links greatly reduce the unwanted collisions that can lead to catastrophic failures. What this simply means is, if you take a large frame, this is a large frame, I recall having mentioned this to you already, but quickly I will write it for you. This is the f, the frequency, and these is the time, and this is one time slot, right. This is one time slot, and it can go on like this. You can have typically 10 millisecond time slots into any number of time slots you can have, and then it repeats again from here, it again repeats from here. Okay, this is a repeat, and if so it can go on like this. If A is communicating to B here, it is possible in the next time slot it may be transmitting from here to here, it is possible, that depends on how it hops, right, and that is a shared understanding between A and B. So, so this is essentially a slot frame, this is called a slot frame, and this is called a time slot, this is a 10 millisecond time slot. You have to be just little bit careful on this name. The slot frame can be of any size, I restricted the size here. So, the slot frame begins all over again here, okay. And how it hopped from here, this frequency, this is f1, this is f2, this is f3, let us say, how it hopped from here. So, it is f2, here it was in if you take it like this, it is time slot 2 comma f2, right, it is 2 comma 2, this is 1 and this is 2. So, 2 comma f2, that means it has gone to this, it has now jumped to 1 2 3 4, 4 comma 3, that means f1 f2 f3, it is 3. So, something like that. So, the sequence is 4 comma f3, I will call it, it can be like this. So, this is how it is hopping, 4 comma F3 and so on. How to hop is a formula which you can easily understand, but anyway this is the main concept behind the fact that it is hopping. So, A and B have to hop together, only then they can continue to communicate and battle the interference problem. Here this picture also tells you that there is no collision, because the time slot is perfectly reserved for a communication between A and B, and this can be of different lengths. Typically it is 10 millisecond, but what is important is to ensure that there is no drift. This time slot begins exactly here. So, you have to ensure that IFT drift is equal to practically equal to 0, right, which is not possible with given the kind of components that we are talking of, crystal oscillators and so on. It is not going to it is not going to work for you that it will not drift, but that is the challenge. You must have a way to compensate the drift. First you should evaluate the drift and then compensate the drift, and ensure that systems in fact come exactly at the same time for communication. So, that is essentially what you should do, otherwise industrial networks where deterministic latencies are required will not work. So, TSCH can accommodate a very dense network, because you can keep increasing the size of the slot frame as I mentioned, and fixed length the time slots also can be changed, right. So, if the slot frame changes everything will change. So, that is a good thing. Now, come to channel hopping. Now, channel hopping is a simple expression here. You can see that the frequency of interest is essentially a function of ASN. This is called the absolute slot number. Now, what is absolute slot number? ASN simply means when the system was switched on, the coordinator sent out the first slot frame at this point. Now, if there are many frames that have evolved, okay, many frames that have evolved, it will tell you when the initial time was started. So, the AS absolute slot number is giving you an indication of when the first slot frame started and the time at which the first time slot started, and you anyway know the current time, then you exactly know how many time slots have passed back, right. You know the current time slot, you know the current time, and from the current time and from the very first time the first time slot started, which is the absolute slot number, you can actually use that with add it to the channel offset and take a modulo of the number of channels. Typically modulo of 16 is taken, I think they choose 16 channels, and you do a modulo of that and you get your corresponding frequency that you want to settle down to, okay. So, essentially you can see that n comma channel offset is what is mentioned here, and I have also put down almost the same thing, an integer value ranging from 0 to 15. The channel hopping, so TSCH can utilize 16 channels for communication which are defined by a channel offset, an integer value which is ranging from 0 to 15, right. This is a number essentially, channel offset is a number between 0 to 15. The TSCH, in TSCH the link between two nodes is defined by n comma channel offset. N, this is essentially this n, this is a pairwise assignment of time slot n, where the two nodes communicate and their respective offsets. So, essentially this when I say A to B, or in this slot frame and A to B in the other slot frame and so on, that essentially is the n comma channel offset. This is a pairwise, A and B are form a pair, and this is a pairwise assignment of the time slot n, where the two nodes communicate and their respective offset. The frequency used for communication can be defined by this expression, in which f should it go is defined by this expression, right. So, so kindly note that this is how the whole system computes, and you can see in this channel 4, equation 4, n channels is defined as the number of channels, and typically it is 16, and some channels can be left out for energy efficiency and all that. So, ASN essentially helps in determining the number of time slots that have elapsed since the beginning of the network. That is pretty straightforward, because the ASN actually contains the start of when the time first slot frame started, and you know the current time as I mentioned. A difference of the two will tell you Exactly that, it tells you the number of time slots that have elapsed since the beginning of the network. The function f can be defined as a lookup table basically, and you can put it up there. Also from equation 4 it can be noted that a different channel, that is n channel, can be implemented over for the same offset for an incremented ASN. The channel hopping mechanism can be utilized with the different frequency over the same link. In other words, you can restrict, you can put n channels as any number that you like, but the whole network should know, that is the key point. You may want to use only 4, you may want to use all 16 and so on. So that part should be made extremely clear. So unless you work on this you may not get a full grip. I just wanted to tell you that PAN, the personal area network formation, begins by what is known as an enhanced beacon which is sent out by the PAN coordinator. The PAN coordinator is the guy who actually switches on the time when the first slot frame also started from there, and the enhanced beacon contains very useful information, channel hopping information, time slot information and initial link information, all of that is held there. Now what is time information? Provides the specific time period at which node should synchronize with the network, okay. And time slot information describes the time when the data will be transmitted. Lastly, the initial link information gives the time on when to listen to an advertising device and transmit to the same device. So all of this information is held in the basic enhanced beacon part which is issued by the PAN coordinator, okay. And this EB keeps getting rebroadcasted as the network starts getting bigger and bigger. The parents essentially will be transmitting the EB. Here you also have to note that links are of two types. I mentioned all this already. There is a shared link and a dedicated link. Essentially this is a dedicated link. It is also possible that A comma B comma C comma D whatever may also want to contend and use this link, in which case it becomes a shared link, and these shared links obviously are prone to a lot of errors because of the collisions that seem to happen there. So I mentioned to you about this is about what Contiki, about what TSCH is all about. I want to point you to the OpenWSN part of the work that has happened in on the web. So if you wish to work on 15.4e, here is a basic implementation. As mentioned here, 15.4e standard defines the MAC and all that it writes. It says time synchronized channel hopping is there, and then this has been implemented. There is something called an IETF c-IoT working group which is talking about how to have IPv6 running over time synchronized channel hopping, and then there is the working group called 6LoWPAN, essentially for an IPv6 packet how to travel over networks of devices communicating over 15.4 radios, that is mentioned in 6LoWPAN and so on. And then there is a routing protocol called RPL, okay, routing over lossy links. There is this protocol called RPL routing protocol, that is essentially a distributed algorithm which finds the multi-hop path connecting the nodes in the network with a small number of destination nodes. So do look up OpenWSN to get more information, but do not stop there. There is also the Contiki implementation of the c-IoT, and I see that there is an IEEE paper, it is called TSCH and c-IoT for Contiki challenges, design and evaluation. Please see if you can download this paper and read it. In this paper, apart from the basic background literature that is described, the challenges are mentioned here, and I would like to read out the challenges if you are planning to implement this c-IoT for any of the industrial networks. First standard is first challenge is it should be standards compliance, right, to ensure that TSCH and c-IoT, all of them, they should interwork quite easily, and only then you can actually say that across vendors it becomes fully compliant and people will be able to use them in a very effective manner. Till date there is not any there are not many implementations of the 15.4e TSCH. So if you want to start, you may still be one of the beginners who would be implementing it from scratch. Now everything hinges on the fact that the timing information is an important thing, because you are saying no collisions because of tightly synchronized systems. Therefore, timing precision is an absolute critical thing, right. So, timing precision is a challenge, and they have to maintain quite a bit of challenge there. Portability, that means if you write that code, it should be supported over you know, any 16-bit 32-bit microcontrollers and so on. So, that is an important thing. Efficiency is also important, because energy efficiency, time efficiency is important, and then of course interface with upper layers, this is an important requirement, otherwise you can't write applications which are you know, easy to get ported. Now related to time synchronization, I want to point you to this little sentence here, which is written pretty well, and perhaps will give you an idea of how tight the synchronization should be. He writes here in this paper is, as I said, this title is 6 TSCH and 6 TSCH for Contiki design challenges. So, let me go down and then look at the challenge related to the time synchronization. See folks, if you put a crystal oscillator, it is okay, it is very good, it is better than the internal RC oscillator, we discussed this last time, but clock drift can still be an issue. If you take a crystal which is 10 ppm range tolerance on the crystal oscillator, synchronization can become an issue. As you can see in this example, if you take 10 ppm, two nodes have a relative drift up to 20 ppm, right. They need not be matching exactly the same way, one of them may be drifting exactly at the time when the other one has stopped you know, has finished. So, it can have a maximum of 20 ppm, which can actually lead to desynchronization. There will be a drift, if you say take 20 ppm, you will have a 20 microsecond drift every second, okay. And if you assume guard times of about 1100 microseconds, which is essentially the default, the independent clocks run out of synchronization after 55 seconds. So, almost every minute you are out of synchronization, even if you put a 10 ppm crystal, okay. So, here note that individual drift is 10 ppm, the relative drift between two nodes is 20 ppm. This is an important thing, and it is written here clearly that it is a relative drift. So, it is not going to work folks. So, you need to have extremely tight synchronization between them. Either you do ACK based synchronization, or you do receiver based synchronization, or you do transmit based synchronization. Moment you receive something from the transmitter, you synchronize with the transmitter, or the transmitter synchronizes after it receives an ACK from the receiver. So, it is either ACK based or it can also be transmission based. You have to make these decisions before you start using them very effectively, okay, and that is essentially what is written in this paragraph. The time source does the time delta computation upon receiving a unicast, and then includes the delta as part of the ACK. So, whenever you are passing the ACK packets and so on, do look at the ways by which you want to resynchronize the clocks, okay. So, do read up this paragraph, which is interesting. So, you can simply compare the reception time against the expected time and adjust the clock, and in the last case what you should do is the time source does the time delta computation upon receiving a unicast, and then includes the delta as part of the ACK, and that ACK is essentially another IE as it is called, and it is sent as part of the information element ACK. Now, when receiving the ACK, what does the node do, the transmitter do? It adjusts its internal clock, and that clock may be adjusted towards backwards with no adverse effect on slot operation, as the time deltas are bounded by 1 TSCH guard time. So, that is a good way to do. You can build on adaptive synchronization and do a lot of interesting things. That is another challenge, and so on, and you can see that the implementation is quite exhaustive. Read this paper to tell you more about the requirements for the 5 challenges that were described above here, and how the system implementation tries to solve this problem. That is all I have for now folks. Thank you very much.